Hey y'all, and welcome back to Alakazam Math Made Easy. In the last video, we went over basically conceptually what a derivative is and how that concept relates to limits. So if you remember, you can find a derivative by saying, all right, I'm going to take the limit as h approaches 0 of the function value between the point x and the point a little bit past x, and I'm going to define the limit because by saying this limit is approaching 0, I'm essentially saying that these 2 points here will become very, very close to the same point. So that's the logic behind this function, right? So going into a little bit more computationally friendly derivative finding, you'll notice that when we did the problems that we solved in the last video, first of all, they took a lot of time. They were mildly annoying because you had to expand everything just to cancel stuff and then cancel it again. So there's a lot of repeated work. And then you figure, like, if this is the same process, there has to be some pattern between all polynomials at the very least, right? There has to be some pattern for polynomials. So these are the two examples that we did last time. The first one was finding the derivative of x cubed, and that returned 3x squared, right? So here's the function, here's the derivative. And then this next function we did was 2x squared plus 3x plus 1. That was our function. And then here's the derivative we returned. So I'll spoil it. There definitely is a pattern, right? And I'll explain the pattern here in a second, right? So the derivative of polynomials will always follow the same pattern, right? And if you look, the pattern will be that you multiply the exponent from the original function to the front. So you multiply the exponent of the original times the coefficient, and then subtract 1 from the original exponent. So following that logic, x cubed, we multiply 3 to the imaginary 1 in the front. That's where this 3 came from. And then we do the exponent minus 1. That's how we got this 2. So the first one follows that pattern. Let's keep going. We have x squared, multiply it to the front. That's where we get this 2. And then we do 2 minus 1 gets us 1. And if you remember from algebra, I guess, this is the same thing as saying it's just x. So that's where that simplification happened. And then moving into x to the 1, remember, if I was just going to take the derivative of x, right, that would be the same thing as x to the 1. I'm going to multiply that 1 to the front of my imaginary, and then multiply it to the imaginary 1 right here. And then I'll do 1 minus 1, which gets me 0. And remember from algebra, anything to the exponent of 0 ends up simplifying to 1. So the general rule is that if you're just taking the derivative of x, right, if it's not x squared or x cubed or whatever, if it's just an x term, it goes to 1 times the coefficient in front of it. So here that coefficient was 1, so it was just 1 times 1. That's where we get this 1 from. But if it was, for example, 2x, it would be 1 times 2, and that would leave us with 2 for the final. And then the last case I want to look at is the case where it's just a constant, right? So if I was going to take the derivative of just a constant, like the number 3, right? I'm taking the derivative of the number 3. That's the same thing as saying 3x to the 0 for the same logic that we talked about up here. X to the 0 is just a constant, right? So if I take 3x to the 0, I multiply 0 to the front, so then I get 0 times 3. And then if I do 0 minus 1, I get x to the negative 1. And then multiplying those together, I just get 0. So the follow-up rule for that is that if you're taking the derivative of any constant, the derivative is 0. So there's 3 different, like, kind of sub rules, I guess. The first one being this general multiply the exponent to the front and then exponent minus 1. The second one is what happens if it's just x, right? Because it's gonna, you don't necessarily write x to 0, so you just write the constant. And this third one is what happens if I take the derivative of a constant itself. And I kind of want to go into a little bit logically explaining these two. So if I'm looking at subrule 2, and I wanted to say, all right, I'm going to find the derivative of y equals 3x, right? That's what this function is. And here's my y-axis, here's my x-axis, and here we go. So why would the derivative of this function logically equal a number? Not another equation, just some number. And that's because, remember, the derivative is the slope of the tangent line. So if I were to draw a line that just brushes up against this, it actually follows the behavior of this line. So what does that tell you? Remember the slope. So the derivative is the slope of the tangent line. And then what does the tangent line help to tell you? The tangent line tells you the instantaneous rate of change, right? So basically what I'm finding by finding the derivative is the rate of change. And a line, by definition, a straight line has a constant slope. So the derivative actually of an x term is just going to be the slope of that term. So there's that. Now let's look at subrule 2. It's very similar logic. I'm sorry, subrule 3. Very similar logic, right? So what we're going to do is we'll say my equation is y equals 3. And so following an extension of the logic actually of the first one is it's a straight line, right? So my tangent line will be the slope of that value, but it's a horizontal line. And we know from algebra, right, that a horizontal line has a slope of 0. So it's the same sentiment as this, where we're taking the slope of the straight line, but because it's a horizontal line, because it's a constant, there is no rate of change, right? The value is not changing when x changes. That's why m equals 0. So those are some general rules. So let's combine a couple things, spice it up a little bit. You can have this absolutely super long, crazy, ugly equation, right? But as long as you follow the same steps, you just do it term by term, right? So this whole equation here, you can just break up into piece by piece. So here we have a 4x cubed, and we've taken our exponent, multiplied it to the front. That's where we get 12. Then we do that minus 1. That's where this x squared comes from. Moving on to the next one, it's a positive term, so we're going to add it. And then 10x to the 7th. We take this 7, multiply it to the 10. That's where the 70 comes from. And then we do 7 minus 1, gets us x to the 6th. Keep going, 12x to the 0. You multiply the 0 to the front, minus 1. That just makes it 0. And then you could have an ugly coefficient, right? Because it doesn't matter what the coefficient is. You would multiply this 1 that's understood to the front, and then you just get that coefficient. And then here's another example with a negative exponent, right? So if I have a negative exponent, I still follow the same process. I multiply that -3 to the front, and now it becomes a -21x. And then I do -3 minus 1. It's getting more negative, so that's why it's -4. So there's that. So basically, the gist is that no matter how ugly the polynomial is, if you take it chunk by chunk at the same time, or chunk by chunk, like consecutively, the rule will be exactly the same. So my recommendation is do not memorize these rules for polynomials, right? Understand it, understand why it's happening. So there's going to be some that you have to memorize, right? So the whole world of functions just does not stop at polynomial functions, right? We've got some weird ones. For example, exponential functions. So like e to the x, right? The good news about e to the x is that the derivative is super, super easy because it literally does not change. So if the function is e to the x, the derivative will also be e to the x. So let's play around with some examples. So y equals e to the x, obviously y prime, that's just the rule, right? That's the rule. E to the x stays e to the x. What let's see, the next one is 7e to the x, and that's just adding in a coefficient, but remember coefficients stay the same unless they're multiplied. And then here we can add an ugly coefficient, and it just, again, still stays the exact same. And then the last one, it does not have to be an integer or like a decimal. It just stays the same because pi is a number, right? So you just treat it like a normal coefficient. So that's the one rule you have to memorize out of the three, right? So exponential functions, that's the first one you have to memorize. But like I said, it's super easy because it stays the same. The next one we're going to move on to is natural log. And if you remember, natural log and e to the x are related, right? Because if I'm going to take the natural log of e to the x, I just get x. So these essentially cancel each other out. So that's how those two are related. So the rule for that one is a little bit more complicated than e to the x because it doesn't say the same, but it's pretty simple, right? So y equals ln of x, the derivative will become 1 over x. So let's jump into some examples so we can see what that looks like in action. 7 times the natural log of x is going to be 7 because coefficients stay the same, times 1 over x, which simplifies to 7 over x. 140 times the natural log of x, like a big coefficient, still rule applies, 140 over x. Pi, still, it doesn't have to be a pretty looking number, turns into pi over x, right? So the goal is every time you see a natural log of x, just multiply the constant times 1 over x, right? That's the rule. And the last one we have to go over is similar to natural log, but it's not quite the same because, give me 1 second, because if you remember, natural log is equivalent to log base e of x, right? So they're similar in terms of what they do, but what changes is this base here. So we're going to jump into some log functions, right? So the rule for a derivative is very similar, and it's actually identical to the rule for natural log, and I'll show you that in a second. So remember when we said that y equals ln of x is the same thing as saying the log base e of x, right? So following this derivative rule, y prime should equal 1 over natural log of e times x, right? But remember, up here we said that the natural log part and the e part cancel, right? So that's going to turn into y equals 1 over 1. This will go to 1 times x. So that's why that's the derivative of the natural log of x. You follow the same rule, you just don't know it. So if it's not a natural log, say it's log base b, you're going to follow that same process, you just have to multiply the natural log of b to the bottom of that derivative. That was a little confusing, so let's jump into some examples. So log base 2 of x is 1 over the natural log of 2. So you take the natural log of the base, right? Here's the base. We took the natural log of it times your variable. Simple enough. Let's add a coefficient. 15 log 3 of x. You keep the 15 because you're multiplying a coefficient. 1 over, you take the natural log of your base again, times x. And then you simplify by just multiplying that constant to the top. ln 3 times x. So again, here's my base. Here's me taking the natural log of it. There's going to be definitely times where the problem looks like this, just 4 log x. And if you remember, anytime log x is written without a base defined, it means log base 10 of x. So basically the issue was base 10 was so common, people were like, I don't really want to write that anymore. So if there's nothing written, it's implied that the base is 10. So that doesn't mean you can just ignore the natural log part in the bottom of the derivative. You actually end up writing natural log of 10 times x. Even though there's not something here, you still have to process the fact that it's implied that it says 10. So that is the principle of how we can find that same definition of a limit in a much faster way for both polynomials and some of the extra exponential or logarithmic functions, right? So if you learned something from this video, please like it. If you want to keep up to date with the videos that I post, when I post them, subscribe to my channel and press the little bell to get notifications to your device. But I guess my parting piece of advice for this topic in particular, don't necessarily memorize the derivative of polynomials, because that you can pretty easily logic through how those rules work. But for more complex ones, like these three, honestly, my recommendation is to write them on a note card and memorize them, right? Because that's the fastest way. And then a little bit of a spoiler alert, at the end of calc, like towards the last third of the class, what we're going to end up doing is starting to do this stuff backwards, right? They'll give you the derivative, like they'll give you 1 over x and ask you to produce the natural log part. So what's really important is to know these special cases, right, in a really intimate way, in the sense that you'll be able to produce it one way and the other way. So that's my recommendation on that. Otherwise, best of luck.